All right, so we're up to module 6, which is risk of bias. So now we're at a point where we have defined the question, gotten the studies, extracted the data. Now we want to start evaluating the data. And we're gonna look right now at the data from each study. And the risk of bias relates to the idea that not all the, sort of think of this as assessing the quality of the study. In other words, how accurate is the study to answer the question that you're interested in answering. So we're going to assess the quality of the studies here and construct tables that will describe that quality. So here's just a little anecdote that one of my colleagues told me a while ago, and it's kind of a funny little story. So in the late 18th century, King Gustav III of Sweden decided that coffee was poison and ordered an experimental study. Of course, this is back in the days when kings could do such things. So what he did was he took 2 convicted murderers, and he condemned one to drink coffee every day and the other to drink tea, and the outcome was death. In other words, the one who died was going to be representative of the intervention that didn't work. And the assessment was 2 physicians were appointed to determine the outcome, I guess, to assess whether the person died or not. So the outcome is that the 2 doctors died first. The king was murdered, and both convicts enjoyed a life. The tea drinker died at age 83. It's not clear when the coffee drinker died. All right, so the idea here is that you have a lot of little studies out there. Obviously, this was kind of a joke, but there's a lot of studies that are very, very small, and you're going to find them if you do a systematic search. And the question is, how much can you believe them? And not even just small studies, but other studies that just may not be done quite as rigorously as you'd like. So in this case, obviously, with this particular study, not only was it small, but it wasn't clear that the 2 individuals were comparable. It also wasn't clear that the intervention was actually done correctly. And obviously, the outcome wasn't something that they could check up on very quickly. So here, the conclusion was that the trial had no effect on the decision makers, and coffee was forbidden in a couple different times, but probably not because of this trial. So people do make decisions based on lack of evidence. And so what we'd like them to do is make the decisions based on evidence, rigorous evidence. All right, so there's no possible conclusion here, and external events and other biases may have confounded the result, and King shouldn't mess with clinical trials. All right, so what are we going to talk about here? We're going to first go over a little bit of terminology, and then we're going to talk about how to assess the bias in each included study, and then we're going to talk about incorporating findings into our reviews. So this is you may have seen this before, this is the sort of typical bullseye representation of the difference between systematic and random error. And so the idea here is that you have a bunch of shots, and in this case, there's both random error and systematic error, because the random error says that you're not always shooting in the same place, you're shooting in different places, so that's the random error. But most of the shots are going to the right of the target, not the left, so you might think there's some sort of systematic error as well, right? There's some sort of bias that causes the person to shoot more to the right, to the left. Now, this is a sample size of 5, so 4 to 1 is not necessarily definitive, but it's an idea here that if most of the shots are to one side, we might actually have a bias. Now over here, we have, again, we're missing the target, but we're missing the target in a different way, right here. So we're always missing the target in the same place. So there's systematic error, but there's very little random error. In other words, we're pretty consistent in what we produce, but it's in the wrong place. Here, we have really good accuracy. We're on the target. There's a little bit of random error, but no systematic error, because on average, we're hitting the right thing. And then over here, we have little random error and little systematic error, right? So what we'd like to be able to do is to disentangle the random error from the systematic error. Now, statistics is very good at working with random error. And it can sometimes be good at working with systematic error if we can actually figure out and model what that systematic error is. But sometimes we don't really know what it is. And so we end up analyzing it in such a way that we account for the random error, but not the systematic error. But then there's other kinds of systematic error, which are not really related to anything we can analyze because the data themselves are inaccurate, right? So if we collect data from a bunch of studies and we collect that data in such a way that it's not an accurate representation of what that study actually did, or it's not a representation of what that study was supposed to have done, then when we combine it with the other data, we're going to get a biased result. So bias in this case is a systematic error or deviation from the truth. It's not the same as imprecision. So imprecision just basically means that you don't get the same answer all the time, or you don't get an accurate answer. In other words, there's a certain right answer, and you don't get that right answer. If you're very imprecise, it means that you don't get close to that right answer. But it doesn't mean that you're systematically going off in one direction. And this is typically reflected by confidence intervals, right? So you have a wide confidence interval, means you don't have a lot of precision in your estimate. But that's not the same as bias. You could have the right estimate in a wide confidence interval. Poor quality is also not bias, because bias can occur in well-conducted studies as well as in poor quality studies, although typically poor quality studies will be more likely to have bias. And not all methodological flaws introduce bias, right? So there's some methodological flaws might cause imprecision, or they might cause you to have a lot of missing data, but they don't necessarily cause you to have bias. And then a final type of error that you'll often run into is poor reporting. So I said this a little bit earlier, that you can sometimes have good methods, a study is well done, but it's poorly reported. And so it appears to be poorly done, but it really was well done. In other cases, you might have a study that is very well reported, but it actually was poorly done. And sometimes the worst case is when the study is well reported, but they've disguised that it was a poorly done study. So, we've all probably been involved with studies where, some things go wrong and you don't necessarily get the chance or need to mention all of the flaws in the study. And every study is going to be flawed in some way. A lot of times these studies look really, really good on paper. And then when people dig into them, they find errors and things that should have been reported that weren't. So why do we care about these biases? Well, first of all, as I mentioned earlier, one of the things that meta-analysis and systematic review tries to do is it tries to figure out what are the different reasons that study results might have varied. In other words, why do some studies come out positive and some studies come out negative, or some studies have big effects and some studies have small effects. And so some of this may be due to bias. It could also be due to other design principles. A second reason is that you might want to give more weight to certain results than others, because you might want to weight the better quality studies better, or you might want to do a sensitivity analysis where you give one analysis you weight certain types of studies, and another analysis you weight all the studies, and then you see what the difference is. Another reason is that if you're making guidelines or rules, you want to not just have an estimate of what the effect is, but you want to have an estimate of how much you should believe the effect. In other words, what's the strength of the evidence? Is the evidence really strong, or is the evidence really weak? So if you have a lot of very poor quality studies, you may actually have a fairly strong effect, but you may not believe it that much. And so your strength of evidence may not be as strong. On the other hand, you might have a few very well done studies, and so your strength of evidence is, you're pretty sure about that result. And finally, the bias may have an effect on your conclusions, right? So if you exclude the studies that are of poor quality, or the studies that are imprecise, or the studies that have the wrong kinds of design, you might get a different answer. So the risk of bias in systematic reviews can operate at two different levels. One is the bias for the individual studies, right? So each of the individual studies has potential bias that you want to assess. And then there's also bias in the methods of the systematic review itself, right? So even if all the studies are good, if you don't analyze the data correctly, or you don't, for example, you have a poor literature search and you miss a few studies, then all the studies might have been good, but your systematic review isn't going to be good. So one warning is that in the past, a lot of people have developed various kinds of quality and risk of bias scales. For example, there was an early one where they looked at 3 characteristics, and I think they were randomization, allocation, concealment, and blinding. And they gave you 0, 1, or 2 points, depending on whether it was well done, poorly done, or unclear. And then they would score this from 0 to 6 by adding the scales up, and then they were using that as a way of either justifying whether the study was good or not, or actually sometimes they would put this into the analysis. They would weight the studies by this so that higher quality studies got good weight. And there's a lot of other scales available, but none of these really are supported by empirical evidence, in the sense that we don't really know that do the studies that have these poor scores on these quality scales actually have poor quality? And secondly, does it really make any difference in terms of the validity of the final conclusion? And another problem is that these scales all come up with different answers. They all have different qualities and different rankings. So studies that are good on one scale may be poor on another scale. And then there's also the problem of numerical weighting. How do you weight these different differences, right? If a study is bad on one scale or on one criterion but good on another criterion, how does that compare to a scale which is flipped, right? Which is good on the other criterion. And so if you give everything 0, 1, or 2 points, you don't know if those relative ratings are really correct. And finally, it's difficult to interpret the score, right? If you have a score from 0 to 6, how different is a 4 from a 3? Does a 4 in which you got 3 1s or 2 1s and a 2 any different from a score that you've got 2 2s and a 0? So basically the rule here is don't use quality scales. So instead, you can use various tools. And so the most commonly used tools probably these days in systematic review is called the Cochrane Risk of Bias tool. And they have various forms of this for whether you're dealing with randomized data or non-randomized data. And what they try to do is they try to look at various domains that they feel are important for quality, and then allow you to rank the studies based on those domains. And then you sort of look overall and see how these studies do relative to each other. So basically, they use 7 evidence-based domains. They review, the review authors then judge whether there's a low risk of bias, a high risk of bias, or it's unclear. And there's various rules that they use for doing this, and there's instructions for how to rate the papers. And so you also have to give support for your judgment. So you can't just rate it low or high. You have to give a reason why. And so you need evidence or quotes from the paper or other sources, and you have to explain your findings. So for example, in a randomized trial, you have a target population that you're trying to come up with an estimate for. And people are then allocated either to the intervention or to the control. And then in both groups, you assess the outcome, and then eventually you might publish the study outcomes. So the first type of bias that you can run into is called selection bias. And so selection bias can involve basically how you select the people in the trial. Are the people selected in such a way that the comparison is fair? So to give you an example of bias in selection, if somebody decided that they only were going to randomize people who looked healthy, or people who looked really sick, they weren't going to randomize. That could be a selection bias, because obviously you're not now selecting from the whole population. Or if, for example, you didn't have allocation concealment and somebody knew that the next individual coming in was going to be randomized to the treated group, and the person looked healthy, and they decided to put them in the control group instead, and then when a very sick person came in, they put him in the treatment group, then that would be obviously a selection bias as well, because now you don't have balance between the groups. So some of the domains that you can run into problems with this is, first of all, is how you randomize the sequences. So are you using a random number generation to do this or not? And so typically what you'd want to do is you'd want to use some sort of a computer algorithm to generate a random sequence of numbers, and then you use that random sequence of numbers to determine who gets which treatment. The allocation concealment, as I said, relates to whether, once you've defined those random sequences, whether you keep them concealed from the people who are actually doing the enrollment in the study. Now, obviously, in certain types of studies, like dealing with animals and stuff, this is not really as much of an issue. This is much more concerned with human studies, where you really want to make sure that people aren't cheating. Then a third type of area that's important is masking or blinding of the participants and the personnel in the study. In other words, do the people who are undergoing the intervention or the exposure, are they aware of what they're undergoing? So some things you cannot blind. For example, if you're going to give people either surgery or medical care, you can't really blind that because people usually know if they're having surgery or not. But in some cases, you can run what are called sham surgeries. So people, for example, there have been acupuncture studies where people either get acupuncture or they get poked, but in such a way that it's not really acupuncture, right? So they think they're getting it, but they're not. And also, you want to blind the individuals who are giving the treatment, because if the person giving the treatment knows what the treatment is, they may act differently than if they don't. A fourth type of domain is the blinding of the people who are assessing the outcome, particularly with subjective outcomes. So if a participant, for example, is not blinded and the outcome is a participant-reported outcome, then the participant may report things differently if they know that they're getting the intervention than if they don't. For example, if you knew that you were in a drug trial, you might report that you were feeling better just because you knew you were getting the drug. A fifth type is we talked about the incomplete outcome data, right? So this is the reporting bias when you don't have all the outcomes. So that's also collected to the selective reporting. So you could either have outcomes that are selectively not reported on purpose, or outcomes that are just incompletely reported because somebody failed to gather the information. Now, sometimes that won't lead to a bias, because if the incomplete reporting is just random, the measurement scale wasn't working or something, that's okay. But in some cases, it can be a bias. For example, if the measurement scale doesn't work, if somebody's very heavy, for example, then that would lead to a bias because you wouldn't measure the heavy people. And other kinds of bias too that we'll talk about. All right, so the random sequence generation, the allocation, concealment, as I said, are types of selection bias because they relate to the types of people who are selected into a study. So the random sequence generation, the importance here is you want to do this before the people are allocated, right? So you want to have this sequence generated in advance, determining a random order of assigning people into an intervention and control group to avoid systematic differences between groups due to selection bias. And the advantage of this, of course, is that it accounts for confounders. In other words, variables that might differentially appear between the two groups that might be related to the outcome. So for example, if you didn't randomize, and if most of the people in your treatment group were young and most of the people in your control group were old, then you wouldn't know whether the difference was due to the intervention or to age, right? So that would be an example of confounding. Sometimes, however, the confounders may be unknown, right? They may be factors that you're not aware of that are affecting the outcome. So those you can't really control for in any easy way, right? Because you don't know about them. So the idea of the randomization is because you've randomized the people, but behind the theory of randomization is that the groups are alike in all ways possible, whether known or unknown, because of the randomization. So the second thing here is that what is defining as low or high risk? So low risk means that basically the sequence was generated in an unpredictable way. In other words, you couldn't predict beforehand how things were going to be allocated. So either they use something like a random number table or a computer random number generator, or they used something like stratified or block randomization, or some kind of minimization procedure, or some sort of low-tech thing like a coin toss or shuffling cards for envelopes or throwing dice. Just something that would make sure that the process was random. So those would, if the report says that one of those things was done, like we used the computer-generated random numbers, you would say that those are low risk of bias on this scale, on this item. The high risk would be ways of generating sequences that were predictable. For example, if they said that everybody born in the first half of the month got the control and everybody born in the second half of the month got the treatment, or everybody who was, and now some of those might be questionable as to which way the bias might go. But for example, if the first part of the month was always to the control and the second part of the month was always to the treatment, then on average, right, the control group is going to be older than the treatment group, so there would be a difference in age. Likewise, if you said that all the males got one and all the females got another, obviously that would be a problem too. But there's other ways that people sometimes do it, like they'll sometimes do alternate allocation, or they'll do something like if the record ID is odd, it's control, and if it's even, it's treated. And so those can be sort of ambiguous as to whether those are really random or not. So those might be classified as high risk of bias as well. And then there's other ways that are completely non-random. Yeah.
When you're looking at data, how often is the data available where you can see what is the study done?
The data won't be available. I mean, you're going to have to rely on the report here.
The most reports give enough information to assess the study.
They should. So this is what the reporting guidelines are now saying, is that when you report these studies, you should say how you randomize the data. That's one of the items on the checklist.
It seems like I've read a lot of studies where they don't tell you.
Oh yeah, no, I'm not saying this is done. And so this is why a lot of them are high risk or unclear, right? Unclear would mean they haven't told you, right? So a lot of them are rated unclear because they might say it's a randomized study, but they don't tell you how the randomization was done. So you can't be sure whether they did it correctly or not. Other times they might say it's randomized and they randomized it by alternate allocation, and then it's not randomized, right? But they thought it was. In other cases, it's completely non-random here. Like, for example, we took everybody who was available between 9 and 5 when we put them in the treatment group, but everybody who came off hours was in the control group or something like that. So there are these other kinds of schemes that are going to be high risk.
Well, give you this report in your research. Do you ever advise going back to the originator and asking them this after the fact?
Yeah, you can ask. I mean, so if you're not clear, one of the things you could search for, you could call the investigators up and say, could you send me your protocol, or maybe even just tell me how you randomized the data. If the study's not too old, you can often get that information. Sometimes older studies, it's kind of hard to find, but yeah. Okay, so the second domain is allocation concealment, which we talked a little bit about this. Now, this is during the allocation of participants. So the randomization happens before the people come into the study or the participants, and this occurs during it. So when a person is recruited to the study, no one can predict which group they'll be allocated to. That's the idea behind allocation concealment. And so this avoids selection bias. And it ensures the strict implementation of the random sequence. So, an example that I often give on this is sort of, what if you were a clinician, you had a longtime patient who came down with a bad cancer, and you knew of a new treatment that they could take, but it was an experimental treatment, and so the only way that they could get this treatment was to enroll in a trial. And so you told them about this, and they said, yes, I'd like to enroll in the trial. And so you're recruiting people for this trial, and let's say you knew somehow that the next person to enter the trial was going to get was not going to get the treatment, was going to get the control, was going to get the placebo, let's say. And this patient is ready to get enrolled in the trial, right? So the scientific thing to do is, well, this is the next person to be enrolled. The next treatment is the control. They go into the control group. But as their clinician, that if they get this control, they're going to die. And you've been this person's physician for a long time, so you obviously are very connected to this. You might have you might be tempted to just say, well, don't enroll now. Well, let's wait till the next one comes up. And then the next one comes up and it's a treatment. And then you say, okay, now you can enroll, right? So the randomization's been done properly, but now the sicker people are getting into the treatment group and the healthier people are getting into the control group. And so what's going to happen when you analyze the data is, because the sicker people are generally not going to do as well, the treatment is not going to look as good as it should. So you're going to have a biased result. Not because anybody's doing something morally wrong. It's just because we're not following the scientific principle. So here, the low risk means that there's an unpredictable, yeah.
So in that situation, if you're a doctor and you're 6 persons in the world that have truth, and you know they're not going to get the treatment, how do you do it? How do you deal with the moral aspects?
Well, I mean, so scientifically, my answer to that is you just make sure that the allocation is concealed so that the person doesn't know who the next person is. So it's a 50-50 chance, right? So then then there's no ethical problem. There's no dilemma, right? Because I don't know which group they're going to go into, so I assign them, and I know there's 50-50 chance they'll get either one. That's the problem with not concealing things properly, is now you lead to these kinds of problems. And no, I'm not an ethicist, so I won't do that. Yeah, well, for scientifically, yeah. So, when is allocation concealment low risk? Well, if there's a central allocation, for example, for that doctor to get that treatment assignment. So let's say this is a blinded treatment. They're going to get some kind of well, even if it's not a blinded treatment, they're going to call up a central number, and that central number is going to tell them, what to do. So somebody else holds the randomization code, and so they're just assigned whatever they are. Now it's easy if it's a drug, because if it's a drug with a placebo, you just get a pill. You don't know what the pill is anyhow. Only the pharmacy that's giving you the randomization code knows that. In other cases where it's pretty obvious, like they're going to get one treatment or another, and you can't really blind it, then obviously the provider's eventually going to know what they got. But in this case, you take some of the moral dilemma out of it. Another way is, sometimes they'll say they use sequentially numbered, sealed, opaque envelopes in which they put like the treatment assignments into the envelope, and then they didn't do anything until the envelope was opened. Or sequentially numbered identical drug containers, for example. Like you have the pills in a bottle, and this bottle is labeled 1, 2, 3, 4, 5, and only the pharmacy knows that 1 is treatment, and 2 is control, and 3 is control, and 4 is treatment, and they know the random sequence. So those would be all things where it's hard to predict what treatment the person got, and so therefore it'd be low risk of bias. High risk would be where it is predictable, where, for example, the random sequence is known to the staff in advance, or the envelopes are not well hidden, or there's a non-random predictable sequence. So the second kind of bias is performance bias, and this relates to the blinding of the participants in the study and the study personnel. So why do you want to blind participants and personnel? Well, this avoids problems where you have differential performance based on what group you're in. So you have potential problems if the intervention groups might get a different treatment. For example, if the personnel running the study are not blinded, and let's say, for example, I'm comparing, so this is a study I worked on. We were comparing Tai Chi with exercise. So the people in the Tai Chi group are in this sort of group structure where they're all doing Tai Chi together. So they're not blinded, and the people doing the Tai Chi are not blinded. And so maybe they are, they're acting in a way that would help. They're being very friendly. There's a communal atmosphere, and so there's a lot of good stuff going on in that room that's in addition to the Tai Chi. Whereas the exercise, maybe they're just getting solitary exercise and they're just being put on the treadmill or something, and so it's not a very congenial atmosphere. And so now the people who are getting the Tai Chi, they're not just getting Tai Chi, they're getting Tai Chi with this sort of group collaboration. And so the treatments are actually quite different, right? It's more than just the intervention. Or there might be different participant expectations. So for example, a study where somebody wants to get acupuncture and then there's a placebo and it's not a sham. And so the people who are in the study really wanted acupuncture. And so if they don't get acupuncture, they're disappointed, and therefore they don't tend to do as well because they're disappointed that they didn't get the treatment that they wanted to get. Another problem is that it could actually lead to changes in the actual outcomes. For example, people might say, well, maybe it's an over-the-counter medication, I didn't get it, so I'm going to go out to the store and buy it. So people in the control group start using the treatment, right? So you get this crossover effect. And this can lead to changes in actual outcomes, right? So people might do better in one group or another than they should have because of these expectations. So to figure out whether a study is actually prone to this problem, you have to be very careful because a lot of the terminology here is very kind of unclear. So you'll oftentimes read the study was single-blinded or the study was double-blinded, and it's unclear then sometimes who was actually blinded, right? Or sometimes you'll even read it was triple-blinded. So does single-blind mean that the participant was blinded, the person giving the intervention was blinded, the person doing the assessment was blinded, and same thing with double-blinding. It's also unclear sometimes whether the blinding was actually broken. So they tried to blind people, but people can try to figure out. So for example, in a drug trial, if you have a placebo pill and you have the treatment, but they only look alike, they don't taste alike, then somebody might be able to figure out, okay, it's got a bad aftertaste, therefore I'm getting the drug, for example. So you don't know about that. And then you also don't know, you also have to consider what's the potential impact of blinding, even if it wasn't feasible for the intervention. Again, sometimes you really can't blind because there's just no way to have two treatments. Like, one is you're getting a pill versus you're doing meditation. There's no way really to blind that, right? You know whether you're doing meditation or getting a pill, but you have to consider the impact of that. Could that have affected the results? The fact that people weren't blinded, right? So is that a high risk? It's not just that did they break the blind or not, but could that have biased the result? So for example, if in some cases the blinding is going to be more serious than in other cases. All right, so what are some examples here of low risk of blinding? There was blinding, and it's unlikely the blinding could have been broken, or there was no blinding or incomplete blinding, but the outcome was unlikely to be influenced by that. High risk would be there's no blinding or incomplete or broken blinding, and the outcome is likely to be influenced. So this is somewhat subjective, right? You have to kind of consider, okay, if the person was able to figure out what they were doing, or if they knew what they were doing, is that likely to have an effect on the result? And in a lot of cases, you could probably make the case that yes, it probably does it might have an effect on the result. But in some cases, you might not, particularly if people are kind of agnostic to which group that they got assigned to. Okay, the detection bias relates to this idea that the person assessing the outcome is blinded to what group the person is in or not. So for example, if you are doing a cardiovascular study and you're reading electrocardiograms, and you know that this person got a certain treatment that you think worked, you might read the electrocardiogram differently than if you didn't know that, or if they didn't get that. Or if you were doing let's see, if you were doing an educational intervention and you were assigning, let's see, whether kids got assigned a long recess or a short recess to see whether their educational performance improved, and the performance was based on an outcome that was sort of subjectively assessed by somebody, then that might be related to which group they were in. If you felt, for example, that the recess was going to have an effect on the thing, it might change the way you assess the outcome. Question?
Like on the previous
yeah.
Likely to influence outcome. It could be something else. I mean, if the placebo effect is so strong and the prevailing effect is strong, how do you assess that it's really not?
Right. I mean, I guess it would be a situation where the outcome was something that the person wouldn't have considered in breaking the blind. For example, I guess if you had a blinded study where you think by knowing the blind, the person would be more or less likely to respond some way to a certain subjective outcome. but you had another outcome, which was like a side effect. For example, did they, so let's see, they're either, so let me take the example of, well, let me take the example of Tai Chi and meditation. So let's say one of the outcomes is, do I feel less pain? So maybe you would say that that outcome would be affected by knowing what group you're in, because the people who are doing the Tai Chi might think they have less pain because they're doing the Tai Chi. But you might have another outcome, which is kind of an adverse effect, which is right. Yeah. Okay. So something that's kind of unreal that the person wouldn't really think of would be a consequence of this, but that you might know might be a side effect, and so it wouldn't be something that they would necessarily differentially report differently, or something which was a very sort of hard outcome, like I don't know, like having a stroke or something like that, which it's not likely that the blinding would affect that. But so let's say you had some sort of an intervention which had a, like, okay, so so some of the treatments can lead to high blood pressure, and they might lead to a stroke, right? So that's an adverse event, but it's not something that somebody's necessarily thinking of, and so the blinding might not actually affect that. Okay, so with the blinding of the outcome assessment, so this is going to avoid detection bias. In other words, outcomes that are affected by knowledge of the intervention received. So again, you have to assess, what the terms are here, and when they say blinding, do they actually explicitly say that the outcome assessors were blinded or not? And do you think it's likely that the blinding could be broken? So again, a lot of times you'll have these sort of studies where somebody will read over a bunch of evaluations and make an assessment. And what you'd like is the people who are making the assessment to be blind to which group the person was in. For example, let's say you're trying, again, a new kind of reading program, and your outcome is how the students did on a final exam, and the students are randomly assigned to either get the reading program or not. You want the person grading the exam, ideally, to not know what group they're in, right? Because if let's say the person grading the exam is the person who did the intervention, then they're going to be biased. They might be biased toward grading the people in the reading group a little bit more easily than the people in the non-reading program. So you'd like to have somebody who's sort of external to that doing the grading. And so remember here also that the participants in the personnel may also be the outcome assessors, because, for example, if it's a participant-reported outcome, if you're asking the student how they did on the reading program or something, and one of the questions was, well, did you find it easier to read this passage after doing the reading program? Then they become the outcome assessor, and so their blinding is the key thing, not some external person. So low risk here would be situations where the blinding is holding, or there's no blinding, but it's unlikely that the measurement that you're looking at could have been affected by the blinding. For example, if the outcome assessment is so, it's determined by certain rules. For example, if it's machine graded, if it's a machine graded test, then you're not going to have a problem here, right? And then the high risk would be where you could have that measurement would be potentially influenced by poor blinding. And so another consideration here is that this aspect of assessing blinding may differ across different outcomes. So remember, we could have different outcomes in studies, and so some outcomes may be more susceptible to this bias than others. And so you can design tables that will allow you to have multiple outcomes and therefore assess the blinding for different outcomes in different ways. Okay, the next kind of bias is the attrition bias. And attrition bias happens when people when you have incomplete outcome data, this could either be because people drop out of a study, or you didn't collect all the data that you wanted to, or the study ended too early. And so when complete outcome data for all participants is not available for your review, you have attrition. This could occur because of loss to follow-up, withdrawals, other missing data, and this can lead to bias. So again, to consider whether this is actually a problem, whether this actually might lead to bias, you need to look at how much data are missing from each group, why is it missing, how are the data analyzed, is there differential missingness? So for example, if you have an outcome and the outcome is missing in 20% of the controls and 5% of the treated, then there's a potential for bias, right? Because there's got to be some reason why it's missing so much more in one group than the other. It might very well be that they did much more careful follow-up of the treatment group than of the control group. Or maybe the treatment group was seen more frequently than the control group, and so there was more possibility of collecting data. If they adjusted for that in their analysis, then it might be that the bias is not as crucial. So low risk types of incomplete outcome data are those where there's no missing data, or the reasons for the missing data are not related to the outcome. So, this is, for those of you who know a little bit about missing data, there's 3 sort of standard missing data mechanisms. One is data that are missing completely at random, which basically means that the reason that the data are missing are unrelated to any aspect of the study. In particular, it's like throwing darts at a board, and wherever the dart lands, it's either missing or not missing. And so it's a complete coin toss. Somebody's just missing data because, well, they happen to get sick on a given day and they didn't come in and they didn't report the data. So that's not usually related to the outcome. But there's other types of data where it will be related to the outcome. For example, I was saying earlier, there's a measurement scale which doesn't work if the measurement is over a certain amount. Well, then there's non-random missingness there because only the high measurements are going to be missing. So that would be related to the outcome. Another type of situation where you don't have to worry too much about the bias is when the missing data are balanced across the groups and the reasons for the missingness are similar. For example, 5% of the data in each group are missing because of withdrawal, 3% are missing because of loss to follow-up, and so forth. You could be reasonably sure that the data are not missing differentially between the groups, and therefore it's unlikely to cause any bias in the comparison between the groups. There still might be some problems with the precision of the results, but it's not going to cause a bias. Or if the amount of missing data is so small that it's not really going to have an effect, right? Even if all the missing data were in one category versus another, it still wouldn't change the answer. And so the high risk is sort of the flip side of that. The reasons for missingness are related to the outcome, or there's imbalance in the numbers or the reasons of the missingness. The proportions are big enough to have a clinically relevant effect. Or if you do an analysis that's as treated, meaning analyzing the data as the people actually got the treatment rather than how they were allocated, you got a different answer, then there's a potential bias as well. Or also, if you, for example, find that the analysis with everybody randomized is different from the analysis as everybody who actually you have data on, then that can be a problem as well. Yes, right. So there could be a bias. I mean, you'd have to think about that carefully. So for example, I'll give you an example. Let's say the intervention is something which could have side effects. And if people have side effects, they drop out of the trial, so you don't get the outcome on them, right? So those are the people. So now you know that the people in the treatment group are more likely to have side effects, right? But you're not actually capturing them in your analysis. So if you think that those side effects might be related to the outcome, then that would cause a bias. Yeah. So the final kind of bias is the reporting bias. And so we've talked about this selective reporting, this idea that you only get the results on certain individuals. You don't get it on others. And it's selectively reported. So some outcomes are reported completely and some might be reported incompletely. So one way that this occurs is things like results that are statistically significant are more likely to be reported. So we know that from studies, particularly with secondary analyses, they will typically be reported if they're significant, but not if they're not. For example, if you're looking at interactions between variables, they're oftentimes reported when they're significant, not when they're not. Or if you have several outcomes, you might report the primary outcome always, but secondary outcomes are only reported if they're significant. Otherwise, they're just left out because they're not really giving you any information. So that's not as much of a problem in a single study, because you can sometimes assume that the non-reported outcomes are just not worth talking about. However, it is a problem in meta-analysis and systematic review, because remember what you're doing in systematic review is you're combining the information from all the studies. So if you're only combining the information from the studies that are positive, then your answer is going to be biased, right? Because it's only going to give you the positive results. So let me give you an example. Let's say that here's a good example. Cardiovascular trials often look at kidney disease outcomes because people with heart disease often have kidney disease. However, the main outcomes in the cardiovascular studies are the heart outcomes, right? So let's say that kidney failure is an important outcome to you as a kidney doctor, and you would like to do a meta-analysis to see how certain type of treatment for, let's say, heart disease or high blood pressure, how that leads to whether that prevents kidney disease. And so let's say a lot of the data that you collect, a lot of the studies you collect were actually cardiovascular studies that actually had reported kidney outcomes. So since the main endpoints in the cardiovascular studies are the heart outcomes, they report all the heart outcomes, but they only report the kidney outcomes if they're significant, right? Because if the kidneys outcomes aren't significant, they're just not going to say anything about it. They'll say this treatment for blood pressure reduces your blood pressure and it reduces the number of heart attacks. But if it doesn't have any effect on the kidney outcomes, they just won't say anything on it. Whereas if it does have an effect on the kidney outcomes, let's say they say it also reduces kidney outcomes, and they might say that because that's sort of an added consequence. So for the individual study, when you're reading that, you see, oh, this medication works really well for the cardiovascular outcomes. It doesn't really tell me much about the kidney outcomes, but I'll just kind of assume that those are probably not important enough for them to report. So therefore, you draw your conclusion based on the cardiovascular outcomes. Now you go to do the meta-analysis though, and now you've got some studies with the kidney outcomes and some without. What do you do, right? Because you could make the assumption that all the unreported outcomes were negative, but then what number do you actually plug in there? So that's the problem with selective reporting. So how do you get around that? Well, it's hard to do, really, because in a lot of these studies, you really have no idea what they were collecting data on. And so it may very well be that they didn't report an outcome because they just never collected it. It could also be they didn't report the outcome because they did collect it and it wasn't significant. And so the only way you can really tell this is by looking at the protocol. If you can come up with a protocol or the sort of full report, or maybe call the investigator and say, did you measure this? Then you can find out which outcomes were actually measured but not reported, which outcomes might have been added as things went along, and how they actually analyzed those data. The protocol or the trial register is really the only way to get that information. So a lot of times you really can't tell whether there's selective outcome reporting because it's just not mentioned in the paper. And without further information, you don't really know what the cause is. And so you might just decide, this is unclear reporting. Now, in other cases, you might, because of your subject matter expert, know that in this kind of study, they probably did collect this data, right? So if they don't tell you about blood pressure as an outcome, but the study had to have collected the blood pressure, then there's potential for outcome reporting bias there. So the low-risk studies are those where the protocol is available, all the pre-specified outcomes of interest have been reported in the pre-specified way, or the protocol is not available, but all the expected outcomes of interest are reported. So you find everything you expect to find there. The unclear risk as I said, is where most studies are going to fall because you just don't have enough information to make a decision. And the high risk is one where you actually have the protocol. They said that they collected it, but then they didn't report it. Or the outcomes are reported incompletely in such a way that you're pretty sure that all the ones that were reported are significant. Therefore, it's pretty clear that those extra outcomes that weren't significant probably weren't reported. So there's a sort of a final domain, which is kind of miscellaneous sources of bias. So you have to have a clear rationale why this might cause a bias. It's not just that the study wasn't really done ideally or properly or at a gold standard. It's just why could that actually cause the answer to change? And so don't include here things like imprecision, a small sample size, because that doesn't necessarily cause bias, that will cause imprecision. Or things like diversity. In other words, they were supposed to give a certain dose, but they didn't give enough dose. That's not necessarily going to cause a bias. It could cause a bias if some people don't get what they're supposed to and other people do, and so you're now mixing two different doses together, and so your effect is smaller than it should be. That can lead to an inaccurate estimate. And then other measures of quality like ethics approval or funding. Studies are supposed to report whether they got approval, and they were approved for this, and what their funding source was. Those could lead to bias, but unlikely to cause that. So you basically keep adding these things to your bias tables, and so again, the low risk studies appear to be free of other sources of risk, and high risk studies could be things where, for example, you have some trials which are crossover trials, which are trials where the person gets, or the individual gets both treatments in an order randomized fashion. So they get the first treatment and then the second treatment, so they cross over. And so that can lead to some bias because if you get A and then B, if A has an effect which carries over into the B period, then the B effect is going to be a combination of the A and the B. And so that estimate may be slightly biased. If you randomize people in clusters, in other words, for example, let's say you're doing a schools experiment and you take all the kids in one school and you randomize them to one intervention, and you take all the kids in another school and you randomize them to another intervention. Then if there's some sort of differential way in which those kids are being recruited into the study, like the kids in one intervention are being recruited more heavily than others, then that can be problematic. For example, let's say the intervention is, okay, we're not going to give, this school doesn't get recess, and the other school does get recess. As usual, you might have kids who would refuse to participate, like if they don't get recess, right? So you could have some bias in that sort of situation too, where the people participating in the study are different. And then obviously you have a bunch of non-randomized studies where because you don't have the randomization, you don't have the quality of the groups. And if you haven't done any kind of adjustment, there are various ways of adjusting for non-randomization, either by stratifying or by analysis. If those haven't been done properly, that can also lead to bias. So basically you get a difference in these groups at baseline. All right, so when you're assessing risk of bias, so we've now gone through all the domains you want to assess. When you're assessing it, you want to have at least two people doing it, again, just like you do in the data extraction. You want this to include content and methods experts, because they'll both have something to contribute. And again, you want to pilot this on a small number of studies to make sure that you're assessing this consistently. And you want to look for missing information. So if you have a lot of situations where you're not clear what the bias is, you can either try to get the study protocol or contact the authors. And we typically summarize all this information in risk of bias tables using one for each study. And then you put in these bias tables, you put your judgment for each domain. And so it's either low, high, or unclear. And you want to, as I said, support your judgment here with instances of why you're judging it that way. and explicitly state if there's no information available. So here's an example of one of these tables. So the rows here are the different studies, and the columns are the different bias measures, the 7 domains that we just talked about, and the colors and the symbols code whether the study is at low risk of bias or high risk of bias or unclear risk of bias. So for example, the first study there, the first 3 items, it has a yellow question mark. That means that it's unclear whether this study randomized its individuals correctly, concealed the allocation, and blinded participants and personnel. The next one's missing, which could either mean that it was not accessible or that they haven't assessed it yet. And then you can see, the rest. You've got another question mark. You've got a red mark, which means that there is a high risk for selective reporting bias. And then it's green for the other bias, means that they didn't see any other biases that were there. So basically with this kind of a table, you have a row for each study, and you can just kind of look at this overall, and you can read down the columns to see which types of biases are particularly problematic. And you can read across the rows to see which kinds of studies are particularly well done. So here, for example, the Morricone study, which is the 5th one down, has 5 greens and 2 yellows. So that's, you can be reasonably sure. Now, a quality risk scale might have actually tried to give you a score for that study, but as I say, we don't generally recommend that. Or the 7th study down there is pretty good. Whereas the 4th study, the Mornikatha study, has 4 reds. So that would indicate there's 4 of these outcome domains or bias domains where we think there's a high risk of bias. And so it's likely that that study is at a high risk of bias. And so if we're, we might want to downweight that study somehow or do a sensitivity analysis excluding it to see whether our results would change. Here's another way you can look at it. Now we don't see it by study, we see it just by domain, and you can see the relative weighting of high, low, and unclear risk of bias here. So once you've done this, and once you're satisfied, you probably want to have a narrative description here of this in addition to the table. In that narrative description, you want to make sure that you address what the potential impact on results is. This could also be, as I say, a sensitivity analysis. For example, you might restrict your primary analysis to studies at low risk based on some of the domains that you think are most important here, or all the domains, and always conduct a sensitivity analysis to see how sensitive your results are to this potential bias. You could also do a stratified analysis. You might, for example, subgroup the high and low risk of bias studies and see if you get a different answer. So one thing that's been found empirically in the literature is that studies that are randomized typically have lower effects than studies that are non-randomized because they're less prone to bias. So you could do that by subgroup analysis or some sort of regression analysis. Okay, so let me stop there. That's sort of an overview of risk of bias. Are there any questions? Yes.
A fairly common one, I think, would be if you have like independent observers doing live observations, but after a while they start guessing based on what's going on, material that they see, like which direction they're scoring.
Right. Yeah, I mean, this is kind of like when people do these kind of post hoc calculations to see whether people actually can predict what group they're in. Oftentimes people are very sure what group they're in and then they're wrong. But the problem there is it's not really whether you're predicting it not right or not. It's what your thought process might have on the way you're assessing things, right? So even if I think you're in the intervention group and you're not, and I'm assessing you, if I think you're in the intervention group and therefore I'm cutting you a break on something, because I think you ought to understand that and you didn't. I mean, a good example is like, so on one of these educational assessments, if you're giving a test and there's a question on the test that was explicitly covered in the intervention group program, but not in the in the control. So for example, let me think of an example here. So let's say the intervention was in a writing class, and the intervention was to teach the students to write with an outline or not. And then you ask a question on the test like, what's the first thing, or describe an important characteristic that you should do when writing an essay. And the right answer you're looking for is, you should first do an outline. And you expect that in the group that's been taught about outlines, but you don't expect it in the other group. And the person gives you kind of an ambiguous answer, where you can't really sure whether they're really referring to writing an outline or not. But if you know they're in the intervention group, then you say, oh, they're probably talking about an outline here. But if they're in the control group, you might say, well, no, they're not talking about an outline because they didn't say outline. So if I think you're in the intervention group, then I might give you the benefit of the doubt there. But if I think you're in the control group, I won't. And so it doesn't really matter what group you're actually in. I'm still got a biased assessment. So that may or may not have a bias on the outcome, but it might my assessment might be wrong. Yeah. Any other questions on it? Okay, so let me move on then we'll do one more module and then take a break. This is a pretty short module. So this is the qualitative synthesis. Okay, so now you've collected all the data, you've assessed the risk of bias. Now, what are we gonna do with it? So now we're over to analyze and synthesize the data. And so before you get into the statistical analysis, you wanna kind of do the non-statistical analysis, the qualitative analysis. Now, in some cases, this is all you're gonna do, because you don't have enough data to meta-analyze. We'll talk about this tomorrow, but basically, if you don't have enough data to actually do averaging, then there's not much point in doing a statistical analysis. You may have only found 3 studies, or you may have found 8 studies, but they're all so different that you don't want to combine them together. You just want to describe them. So the qualitative analysis, or the synthesis, is going to summarize the results without calculating the summary estimate of effect. You're not going to summarize the answer in one number. You're just going to give an overview of what the studies found, and then you're going to synthesize this textually to try to explain. It's sort of like in the old-time narrative review, but in this case, you've done a systematic review. As opposed to a quantitative synthesis where you're applying statistical methods for calculating a summary estimate of effect. So you don't want to do a quantitative synthesis when you're so-called mixing apples with oranges. In other words, if you have a bunch of studies which are each addressing kind of different types of questions, or they have slightly different populations or slightly different interventions, or slightly different outcomes. Now, if you've defined your question well, this is going to be less likely to happen, but you could still have some wiggle room. So even if we go back to our kidney question from the morning, where we were trying to figure out which type of dialysis was better for people with chronic kidney disease, if it turned out that some of the studies were done in the United States in the 1990s, and other studies were done in China in the 2010s, we might decide, well, we don't really want to combine those studies because they're at different time periods, they're in different countries, they're probably using different techniques, there's different types of care, there's different types of healthcare systems. And so all those sort of things might lead us to believe that we really shouldn't be combining these things. Or we might decide that there's so much subjectivity in the outcome that we can't really be sure that they're all measuring things the same way, or maybe they've explicitly measured things on different scales. And so they can't really be combined. So if you combine a broad mix of studies, it answers a broad question. So the example I gave this morning of the psychotherapy, by combining all psychotherapy studies, you might know whether or not psychotherapy works on average, but you might not know what type of psychotherapy works for what type of people, and so it may not be very practical an answer for you. And so the answer may be quite meaningless. But this will vary by discipline. So as I said, in medicine and healthcare, the questions are much more specific. In social science, I found that they're much broader, and they tend to find many more studies. So for example, they might be looking at any kind of a reading program versus a specific type of reading program for a specific type of student, a specific type of environment. All right, so here's some examples. So would you combine these studies? One is looking at early light reduction to prevent retinopathy of prematurity. This is a situation that happens in premature infants where their eyes don't focus very well. And so one of the early treatments is to try to make sure that they're not exposed to too much light early in life. And so here are the 5 studies that were collected. One was conducted in 1997, one was conducted in 1952, the others were in the late 1990s. The average weight of the infants, so it's not an average here. All we know is that all the infants were under a certain weight. And then the interventions themselves varied from the amount of time for what how the light was restricted, whether they got goggles or a patch, for how long they were restricted. So the first one restricted the light using goggles from 6 hours of age to 31 weeks of age. And the second study put a patch on an eye and only looked at 24 hours. The next study looked at a patch on both eyes and looked from birth to 32 weeks and so forth. So the question is, if you had the outcomes that you wanted in all 5 of those studies, would you average them together to come up with an answer? And people would do this in different ways. The important thing is to report this kind of table so somebody who's reading it can make their own decision. Some people might argue, well, there's not enough difference here. These are all premature infants. They're all having light restricted. You're looking at reasonable amount of time here. You might exclude the second study because it's an early study and it's only looking at the first 24 hours. But the other 4 studies are fairly consistent, right? From the first day of age to about 32 weeks. And there's either a patch or goggles. You might not think that's really makes much of a difference. And the weights are, well, they range between 1,600 grams and 1,200 grams, but you might think that doesn't make too much difference. It might also be that you could get subgroups in some of these studies so that you could, for example, find the subgroup that's less than 1,200 in all the studies. So there might be various ways of kind of working around this to figure out whether to combine the studies. But you might also decide that they're too different and you just don't want to combine them. So the meta-analysis is only as good as the studies in it. And so if the included studies are biased, then obviously the meta-analysis result will also be incorrect. It might actually give more credibility to a comparison than you should have. In particular, if things are underestimated, if uncertainty is underestimated, then your confidence intervals may be too narrow. And if you have serious reporting biases present, then you might have an unrepresentative set of studies that give a misleading result. Like you have all the positive studies, but none of the negative studies. So oftentimes you can't do a meta-analysis because you don't have enough studies. They're dissimilar. They're methodologically diverse. There's other factors that differ between them. They use different outcomes and they report them on different outcome scales. And so in this case, probably the best thing to do is just to summarize each study separately and comment on the results and try to synthesize them qualitatively by saying, most of these studies seem to be positive. And even though I can't give a definitive estimate of how positive they are, they're all sort of trending in the right direction and shows that this intervention either does or doesn't work, or there's enough heterogeneity here that it's not really clear what the overall estimate is, but I can say that there's some heterogeneity. And so therefore, there's more research that needs to be done because we need to figure out this study was very positive and it was looking at this particular subgroup. And so it might be that this intervention works really well in the subgroup. We need to study that more. So qualitative synthesis is just an assessment of the evidence that goes beyond the factual descriptions or tables that you put together that simply tell you how many studies were assessed and the inclusion and exclusion criteria and the sample sizes and the treatments compared or the quality. So those are all important tables to put together. So for example, this kind of table here is very important to have that tells you, and this risk of bias table back here is very important to have, but that's not enough. You have to actually summarize this for people, and you want a structured summary, description, and discussion of all the study's characteristics, and then put that together in the context of the cumulative evidence to decide, okay, is this intervention working or not working? So here's a quote from an old paper. Meta-analysis was developed to replace the artistic narrative review with a scientific and systematic method. Yet in fear of allowing bias to creep in, meta-analysis is typically mechanistic, driven more by concerns about reliability and replicability than about adding to understanding of the phenomena of interest. So the idea here is that you can't just sort of turn the crank and say, all right, well, I've got my flow diagram to tell you how I collected the data, and here's my risk of bias table, and here's my table of description of the study characteristics, and here's my meta-analysis or my plot, my forest plot or whatever, and here's the answer. You actually need to put some context here, and you need to talk about to what individuals this or what types of people this result applies, how much you believe these results, and how supportive these different studies are of the result. So you want to orient the reader to the scientific background, describe what happened to the study participants over the course of the studies, critique the strengths and weaknesses of the evidence, identify the differences in the design and execution of the studies that may explain why their results differ, and describe how the design and execution of the studies affects their relevance to real-world settings. All right. So basically, you are the expert. You are saying, I've done all this research. I now know this body of evidence, and here's what I know about it, and here's what's important, and here's what's not important. You want to integrate this general summary of evidence and potentially subgroup analyses based on the setting and the patient populations. Call attention to those populations that have been inadequately studied or for whom results differ. Describe how the systematic review findings contrast with conventional wisdom, and interpret and assess the robustness of the results of a meta-analysis, for example, if conducted. Right? So this is just, again, putting it into the context of the evidence that you have. So a good qualitative synthesis should describe the nature of the evidence and interpret its possible effect, the possible effect of the differences among the studies, so the different ways the studies are designed, the different results the studies find, the different populations that they look at, and how that might affect your overall conclusions. You want to evaluate the strengths and weaknesses of the evidence base. So how much can I really believe these findings? How strong are these studies? And then you want to conclude about, how can I combine these things? What are some of the nuances? What do I need? What do we need to know more about? What are the gaps in the literature? And what are the future directions that this research should go in toward? And it may very well be that you conclude that we know very little. I mean, a lot of our reports, the conclusion is there's really not very much conclusive evidence. So people typically don't undertake a systematic review unless they think there's some evidence out there that they can actually draw a conclusion from. But surprisingly, what we often find is that the evidence is so poor, or it's just so randomly designed that we don't really know as much as we think we do. So for example, there's one study that studied kids of a certain type, and another study studied adults, and another study looked at people in one country, another study looked at people in another country, and we don't really think that any of those things are really enough to be able to give a synthesis that actually makes sense. All right, so let me, as I said, that was a short module because there's not a lot to say about qualitative synthesis other than, try to summarize what you've found. But yeah, question.
It seems to me like the way that your systematic review process is getting us to quite a narrow set of quite complicated in terms of obviously.
Mm-hmm.
And I'm wondering, so I'm coming from an active science background, so I'm wondering whether there's how we might integrate different kinds of steps and studies into a single. So for instance, if we wanted to find some threshold of exposure out of a more epidemiological context, you might imagine that you would have population studies, spatially, and maybe actual experimental studies also to be able to get some
Mhm.
and to put those different kinds of information into a metric.
Right.
Which is a different kind of, essentially, you might use the Pico framework on those two different subsets of information to come up with still a synthesized knowledge.
Right, right. Yeah, so I mean, a lot of times you will have sets of studies which are really of they're different types of studies, right? And they may each provide you with information about the question that you're interested in. And they may not really be amenable to combining in the sense of statistically, because they're sort of approaching things with different types of analytic frameworks or analytic procedures. So it might be that you have to kind of synthesize them separately, and then if they both kind of come to the same conclusion, you can reach a qualitative conclusion that they're supportive. Sometimes you might be able to figure out a way to kind of put them all together into one analysis. But the qualitative synthesis is more just saying, well, it's more subjective in some sense, because I mean, when you do a meta-analysis, when you do statistical analysis and you use certain techniques, there's obviously the subjectivity of what technique you're using. But then once you've decided on the technique, you just go through the process and you come out with an answer. And how you interpret it is somewhat subjective. With the qualitative, it's much more subjective, because your interpretation of it may be very different from somebody else's. So the important thing in the reporting is to be transparent on what you found, so that the person who's reading it has all the information available. And but it is important that you assess it for them, because for the reader, because you're the person who's looked at the information, and so they can't really know what you know about the data. I mean, there's not really a one right way to do it. But it is very difficult when you have data coming from different sources and different, that are collected for different reasons, really.
Have you ever been in a situation where you started out with meta-analysis, and then when you look at the data, a year later, you don't have
Yeah, I mean, I don't know. I typically get called into these things when they've collected the information, and so they want a statistical analysis. So I don't know if I can say. I mean, I personally have been in that situation, but it certainly happens quite a bit. A lot of the evidence reviews we do, as I say, they're big projects, and so they may have multiple questions and multiple outcomes. And some of those questions and outcomes can be analyzed quantitatively, and some have to be analyzed qualitatively, just because you don't have enough information. So you might think, there have been cases where people thought there were a lot of studies, and then when they went and tried to collect them, they found really that they were all excluded for some reason or another. And maybe they were interested in randomized studies and they found they weren't randomized, or maybe they were interested in studies that looked at certain populations and they realized that the population studied were mixed populations, and so they couldn't really say that they were all of a certain type, and so they excluded those studies. So that does happen quite a bit, that you can't do what you want to do. Any other questions? Shall we take a break now? Okay. So we've got 2 more modules left. So the next one is meta-analysis, which will just kind of be, for those of you who aren't coming tomorrow, this will be a quick overview of meta-analysis. For those of you coming tomorrow, it's an introduction. So you can think of it like a preview. All right.